In this video, we'll continue our discussion of determining the truth of statements in first-order logic, and in particular, we'll consider some examples with negated, nested quantifiers. And I want to mention again that in order to determine a truth of a statement in first-order logic, we have to specify the universe of all the variables. We must understand what the values of the predicates would be, and if there's any functions or constants that are being used, we should also understand what those values are in the universe of the variables. So now we want to consider the following formula in first-order logic and determine whether it's true or false. And I want to mention that either a statement is true or its negation is true, but not both. So we are first going to practice the negation and then consider the statement of the negation, whether it's true or if the original statement is true. So for this question, we're going to let the universe of all the variables x, y, and z be the integers, and our predicate p of x, y, z will be x plus y equals z. And we need to consider, if we understand the functions that are being used, there's no constants, and we understand what x plus y means for the integers and also equals for the integers, so we're fine with that. And we also see that all of the variables are integers, so we understand the universe of the integers and all the predicates, so we can consider the truth of this statement. So first, well, let's practice again what it means to negate quantifiers. So we have to negate there exists becomes for any. For any becomes there exists. There exists becomes for any. And we have to negate the predicate. And you'll notice that all of the variables in this formula are bound. Okay, so it's saying that for any x, there exists a y such that for any z, x plus y does not equal z, is what it's saying. So for any integer, there exists an integer y such that x plus y does not equal z for any integer z. So let me just write that out. So this is negation. So for any integer x, there exists an integer y such that for any integer z, x plus y does not equal z. Okay, now let's look at the original statement. So that's saying this one was there exists an x for any y, there exists a z, p, x, y, z. And I'll just write that as a statement also. There exists an integer x such that for any integer y, there exists an integer z such that x plus y equals z. So now we want to determine which of these two statements are true. So basically, for any there exists an integer x such that for any integer y there exists another integer z which equals their sum. Well, we could actually strengthen this statement to be stronger, because for any x and for any y, there exists an integer z that equals their sum precisely, x plus y. If we just set z equal to x plus y, we have an integer that equals their sum, so this statement is true. And because this statement is true, its negation must be false. And when I strengthened it, I was just saying that for any pair of integers, their sum is an integer. Now let's consider logical equivalences. And we see that statements involving quantifiers and predicates or formulas are equivalent if and only if they are true under the same model of interpretation. And a model of a formula is an interpretation for which the statement is true. And a satisfiable formula has a model. So statements are equivalent if and only if they're true under the same interpretation. And that would mean that no matter what the predicates are or the domain of discourse, they would have the same truth value. And I gave an example of two equivalent statements here. So P of x is the statement that we are negating for any x R of x. And Q of x is the statement that there exists an x such that not R of x. So this was what we use when we negate quantifiers. So these are logically equivalent. And we can see this by considering a specific example, but recall that regardless of what the predicates are, this would have to be the case. They'd have to have the same truth value. So just as an example, so let x be the integers and R of x be the statement that x is even. So Q of x reads, there exists an integer that is not even, and if we negate the statement for P of x, so it's for any x, R of x, that's saying any integer is even, and when we negate that, there is an integer that is not even. And you can check if statements are logically equivalent by considering whether they would have the same truth value with different predicates and different domains of discourse or specific domains of the variables. Now, a theorem in predicate logic is a statement or a formula that is true for every possible interpretation. So we consider it a theorem or a valid formula if it is, and only if it is true for every possible interpretation. So an example of a formula is that for any x in some universe or set S, either the predicate x is true or its negation is true. This is a tautology. So either the predicate x is true or its negation is true for any value x. Now, if we consider the following statement, for any x in S, negation of the predicate x, or for any x in S, P of x, we can assess that this is actually not a theorem. And the way that we can tell that is we can give a specific universe for the variables x and specific predicate in order to show that this statement would not be valid or true. And the way that we can do that is let x be the integers, and let p of x be the statement that x is prime. And just to contrast this, so for the theorem, it would say for any integer, the integer is prime or not prime. But when we have this second statement, we have any integer is not prime, or any integer is prime. And both of those statements are actually false. And when we take the disjunction of two false statements, the statement is false, the over is false. And how do I know this? So 3, for example, is an integer, but 3 is prime. So for this statement, the counterexample, or any other prime number. And for this example, we can just have our counterexample be 4. Is an integer, but 4 is not prime. So because of this, we found a counterexample to each of those statements, so we know that their disjunction is also false. So that is a way that we can tell that this is not a valid formula or a theorem.